Hi and welcome back. Today we're going to discuss Chapter 18 in versions 1 and 2 of Klein Organic Chemistry, which is also Chapter 17 in version 3 of Klein Organic Chemistry. Today we're going to talk about aromatic compounds, and we'll discuss their features, how to recognize them, and a couple of reactions that can happen not on aromatic compounds themselves, but at the benzylic position. So aromatic compounds, or sometimes they're called arenes, include benzene and benzene derivatives. And so benzene is shown here. That's a six-membered ring. It has 6 carbons with alternating single and double bonds. Next we have toluene as an example, which has a methyl group attached to essentially a benzene ring. And then here we have xylene, which has 2 methyl groups attached to a benzene ring. This is orthoxylene, and we'll talk about that a little bit later on. And the reason we have the name aromatic is because many of these were originally isolated from fragrant oils, and so many of those fragrant oils contain aromatic moieties, and that's where the term aromatic comes from. But not all aromatic compounds have a fragrance. Many of them are odorless, and they're quite common. They're found in a lot of everyday products. They're found in medicines and in natural products. So a lot of drugs have aromatic moieties as well. Here we have Nexium. We can see an aromatic ring here. And here we have Zoloft, and we have a couple of rings, for example, here. So coal also contains aromatic rings fused together by other non-aromatic moieties. So the aromatic rings here are in orange, and the non-aromatic moieties are in gray. All right, so benzene is the name for is a parent name for a monosubstituted benzene derivative. And so if you have something like a chlorine attached to a benzene ring, then that's chlorobenzene. If you have a nitro group attached to a benzene ring, then we have nitrobenzene. If you have an ethyl group attached, then we have ethylbenzene, for example. And sometimes these monosubstituted benzene rings can have common names as well. Here are some that you should probably commit to memory, and I'm going to only ask my students to memorize a few of these, but you will need to know some of these because they are used as parents for other aromatic compounds. So if you have this moiety, let's take this one for example, phenol or phenol, can be pronounced both ways. If you have this OH group on a benzene ring, this moiety in your ring, and then you have some other substituents on it, then you can use phenol as a parent for that compound. We're going to look at some examples of that in just a little bit. So I want my students to learn toluene, phenol, aniline, of course benzoic acid. They should already know that one. Benzaldehyde, which is pretty obvious. I mean, that goes without saying. So benzoic acid, benzene ring with an acid group. Benzaldehyde is a benzene ring with an aldehyde group. Pretty easy. And then I don't expect my students to memorize anisole, acetophenone, or styrene, but those are good ones to commit to memory anyway. Styrene is where the polymer polystyrene is derived. So in general, if a substituent is larger than the benzene ring, then the substituent becomes the parent, such as in 1-phenylheptane. So here we have a 7-carbon chain attached to a benzene ring, and the benzene ring in this case becomes a phenyl group. So if a benzene ring is a substituent, it is a phenyl group. If we had a shorter chain here, then say it was 3 carbons long, then we would have a propylbenzene. So it depends on which is longer. But that isn't always true. Sometimes it matters whether it's just easier to say. So if you have something like, for example, this molecule, which is pretty big, okay, so this molecule here is named as a derivative of ethane because we have 2 carbons here. Okay, and so the parent is actually ethane just because it's easier. So this molecule is para dichloro, okay, diphenyl, because we have the two benzene rings, trichloro, trichloroethane. And so what this molecule is actually DDT. So because it's easier to name this as a derivative of ethane, then we go ahead and do that because it's just easier. So sometimes this rule doesn't actually hold. Now, I wouldn't really give my students this molecule and ask them to name it because it's pretty complicated, and you would just kind of have to know how that was named. But a phenyl group can also be abbreviated with a pH, like as in this molecule here. This is tetraphenyl cyclopentadienyl, and you can see here that the cyclopentadienyl is smaller. The cyclopentadiene ring is smaller than a benzene ring, but it's still used as the parent for convenience in this case. So the phenyl groups can be abbreviated as pH, or they can also be abbreviated sometimes just with a phi symbol. I don't generally do that. I rarely do. Sometimes I will abbreviate with pH. I don't generally use the phi symbol. Alright, and so if you have two methyl groups on a benzene ring, then that can be, the common name for that is xylene. So these are the xylenes. So this is orthoxylene because these substituents are just one carbon apart. They're just adjacent to each other. And if you have a benzene ring that is substituted at the 1,2 position, then it's ortho. Okay. If you have a benzene ring that is substituted at the 1,3 position, then it's called meta, as in metaxylene here. That's at the 1,3 position. And if you have a benzene ring that's substituted at the 1,4 position, then that's called para, because the substituents are at carbons 1, 2, 3, 4 of the ring. So here we have orthoxylene. This could also be called 1,2-dimethylbenzene if you want to name that as a benzene derivative. Here we have metaxylene, or 1,3-dimethylbenzene, and here we have paraxylene, or 1,4-dimethylbenzene. Alright, so to name a benzene derivative, what do we need to do? We need to identify the parent chain, which is the longest consecutive carbon chain. Identify and name the substituents, and we're going to assign those alphabetically. Number the parent chain and assign a locant to each substituent. And give the first substituent the lowest number possible. And then arrange them alphabetically and assemble the whole name. So don't forget the parts of a name of an organic molecule, and those still hold true here. Parent goes in the middle, substituents go before the parent, and the stereochemistry goes out front in front of the substituents. After the parent, we have potentially unsaturation, if it's there. Now, we don't count benzene derivatives as unsaturation as far as naming. And then we have functional group. Okay, so these in general still hold for organic molecules, and this is the way you arrange the parts of a name of an organic molecule. Okay, so what about this? Let's identify the parent here. Now don't forget, this is one of those special compounds that I asked you to remember. So this is a derivative of phenol or phenol. And so because this is a derivative of this parent, which is phenol, we have to give that OH group that's on our parent, the functional group that's on our parent, the number 1, because it's on the parent. It's our main functional group that's going to go at the end of our name. Okay, and so that has to get number 1, priority number 1. And so then we can start naming, giving our second substituent the lowest number possible. It doesn't matter in this case, so we can just go 2, 3, 4, 5, 6. And so what are we going to call this thing? It's going to be, we have dibromo 3, 5 dibromo phenol. Okay. Okay, so this just goes on about how to name that, and we've already done that. Alright, so let's name these molecules here. So see if we can identify the parent. The parent for, let's go ahead and get a lighter color here. The parent for this molecule is in black. The parent is benzaldehyde. Okay. The parent for this is also in black. They're all in black. This is actually toluene. Yeah. Okay. And the parent for this is here, which is anisole. Okay. So now we're prepared to name these. The first one, we have a chlorine attached to this benzaldehyde parent, and it is at the 4 position, which means if it's 1,4, then it's para. Okay, so we could say para, and if you have para, you can just abbreviate that with a P, or you can say para. Now we can say para-chlorobenzaldehyde because the 1 is understood to be at the position of the benzaldehyde group. Okay. All right. So next we have the toluene. Okay. So here we have 1, 2, 3. So we have meta, bromo, toluene. And you could also call this as a derivative of benzene, but I'm going to stick with parents being those special compounds I asked you to memorize. Now, I didn't ask my students to memorize anisole, but we can, I wouldn't give my students this, but your professor may have wanted you to do that, and so here that gets number 1, and the nitro is 2, so that is ortho nitro anisole. Okay. Alright, now I have a whole bunch of ones to name here. I may not name all of them, but I'll pick out a few and we'll name them. So the first thing we're going to do is look for the parent. And this isn't necessarily finding the longest carbon chain here in these benzene derivatives. Remember, we want to find the parent that I asked you to memorize, one of those parents. So match it up with one of those parents that we had up here. Okay. All right here, okay? So toluene, phenol, anisole, aniline, benzoic acid, benzaldehyde, acetophenone, and styrene. All right, and so here we have a derivative of benzaldehyde. Okay? So this is going to be at the 3 position, we have an isopropyl group. So that means it's meta. So meta, we could just say meta. Isopropyl, benzaldehyde. Okay, and here we have in the ortho position, we have a bromine. Okay, so this is ortho, bromo, toluene. Okay, here we have a phenol parent or a phenol group, a ring. So that's a derivative of phenol. And here we have, that's going to be number 1. So we want to give our next substituent the lowest number. So that's 2, 3, 4. And we can't use ortho, meta, and para here because we have more than 2 substituents. And so we're going to have to say 2, 4 dinitro, okay, phenol. All right, this next one does not match any of our parents that we learned, and so therefore we're going to have to use just benzene as our parent. Benzene, okay? So let's alphabetize these guys. We've got isopropyl and we've got ethyl. Okay, so let's give this one. Let's see if let's give our substituents the lowest numbers possible. 1, 2, 3, 4. Let's try a couple of different ways. 1, 2, 3, 4, 5. I think we're going to have to go along the black path. Okay, so that's 2 ethyl, 1, 4 isopropyl, benzene. That doesn't look very good. I'll go ahead and erase that. Okay. Okay, so next we've got a bigger one, and let's see what we can do with this one. So can we identify a parent here? We can. The parent is phenol. Okay, so let's go ahead and write that down. All right, and that parent includes our functional group, so that goes at the end. Now we want to give our substituents the lowest numbers possible. So if I could go this way, 1, 2, 3, 4, 5, 6, and it really wouldn't matter, except that if we go this way, 1, 2, 3, 4, 5, 6, along the black path, our ethyl group is going to come at carbon 3. And along the yellow path, our isopropyl group will be at carbon 3. Well, ethyl comes before isopropyl alphabetically, so the better way to name this would be along the black path. Okay, so let's alphabetize these guys. So we've got bromo, so that's 2, 6 dibromo. Okay, oops. And then we've got 4-chloro, 3 isopropyl, and I'm sorry, no, 5 isopropyl. We've got 3 ethyl. Okay, so B, C, the ethyl goes here, and then the isopropyl comes last. So this is a big one. So we've got 2, 6 dibromo, 4-chloro, because we're going to alphabetize these, right? Chloro, 3 ethyl, 5 isopropyl, phenol. So that's a tough one, but it's not really that hard if you assemble it strategically. Alright, so let's talk about the structure of benzene a little bit. August Huckel in 1866, he's the one who first proposed the structure of benzene, and he said that a benzene ring is comprised of alternating single and double bonds, and he was right. They are alternating single and double bonds, but he thought that a benzene ring flipped back and forth from a conformation like this to a conformation like this, where the bonds flipped from, say, being here to being here. And he was really close, but the truth is somewhere in the middle. It's actually a resonance structure. What we have is resonance between these two structures, where the 6 electrons that are contributed by each one of those carbon atoms are actually delocalized around the ring. So think about that. Each one of the carbons in a benzene ring is contributing 1 electron to that pi system. In other words, there's an electron between these first 2 carbons. There are 2 electrons between those first 2 carbons that are shared, forming this double bond. There are 2 electrons, one donated by each carbon for this double bond. There are 2 electrons here donated by these 2 carbons. Okay, each donates 1 electron. And so the fact is the electrons don't know where they belong because of this resonance structure that exists, and therefore all 6 of those electrons are simply delocalized around that ring. And so the rings represent resonance structures. They represent the delocalization of the 6 electrons from the benzene ring. So some people represent benzene with just a circle in it to represent delocalization. Now, I don't generally do that. I generally draw them out, but some people actually prefer to do it that way. So we can see the special stability that benzene has by comparing reactions that it can undergo with simple individual double bond compounds. So if you have something like cyclohexene, which you produced in lab this semester, then actually that was last semester, right? Yep. So then cyclohexene can have bromine added across it in an anti conformation, right? And therefore it reacts really readily with bromine. But if we try to add a bromine across one of the double bonds in benzene, we get no reaction. We're going to see in the next chapter that we can actually get a reaction with bromine, but it's not an addition reaction. We're going to actually get a substitution reaction, and we're going to have a catalyst and a lot stronger conditions. So let's consider this problem, and this is problem set 18.6 in the older text and 17.6 in the newer text. This problem says compound A is an aromatic compound with the molecular formula C8H8. If we treat this compound with an excess of Br2, compound A is converted into compound B. Okay, now we have C8H8Br2. Identify the structures of compound A and compound B. Well, it looks a little bit more complicated than it is. What they're saying is that we're going to react this with Br2, okay? And we're going to have some kind of double bond, and we're going to get an addition reaction of bromine across that double bond, okay? And then the rest of this molecule is just something attached to that, right? So we got to figure out what the R's are, okay? If there are both R's, they may not even be both R's, right? So we're talking about aromatic compounds, and what do we know about benzene? Benzene is C6H6. What does benzene look like? Benzene looks like this, okay? It's C6H6. There's one hydrogen on each one of those carbons because they're sp2 hybridized. Since it's sp2 hybridized, each carbon, remember, can have four things attached. This carbon has each carbon can have four bonds, So this carbon is double bonded to another carbon, so that's two bonds. It's single bonded to this carbon, so that's three bonds. And it has a hydrogen, so that's four bonds. So each one of these carbons only has one hydrogen on it, giving it the molecular formula C6H6, okay? So for C8H8, what would we have? We'd have a benzene ring, okay? And then something else attached, just two more carbons with two more double bonds, okay? And so this compound looks like this, okay? So since we pulled a hydrogen off here, this is an isomer, so the hydrogen ends up over here. We didn't actually pull it off. I mean, it's just an isomer of that. If you consider that we attached something here, the hydrogen has to go somewhere else. So this compound is C8H8, and if we add bromine across it, what do we get? We get bromine and bromine. Okay, so that is the products. This is compound A, this is compound B. Alright, so let's consider the special stability that aromaticity lends to benzene. Okay, if you take cyclohexene, for example, if you add hydrogen to the double bond, if you perform hydrogenation, then we get out 120 kilojoules per mole of energy for each hydrogen bond. We get 120 kilojoules per mole of hydrogen bond for each double bond. We get 120 kilojoules per mole of energy for the double bond, okay? To hydrogenate that double bond and get cyclohexane. If we have two double bonds, notice that these are conjugated, and we hydrogenate both of them, then we get out a little less than twice the energy that it takes to hydrogenate a single individual double bond, okay? So it would be 240 if it was double, but you see we get 232, so not quite double. We would theoretically get about 3 times the 120 for this theoretical molecule here, cyclohexatriene, and we would expect to get 360 kilojoules per mole out. But in fact, if you do hydrogenate benzene, which is in fact difficult to do, you will only get 208 kilojoules per mole of energy out. And that's because since benzene is aromatic, it's particularly stable, and we get less energy out when it's hydrogenated, okay? So hydrogenating benzene gives us only 208 kilojoules per mole. The difference between benzene and this theoretical cyclohexatriene, if we were able to hydrogenate all three of those double bonds in that molecule, is 150 kilojoules per mole, 152 kilojoules per mole. That's the theoretical stabilization energy for benzene. So it's that much more stable than it would be if it were not aromatic. All right, so if we have a molecular orbital diagram, we can consider aromaticity. So remember, right down the middle of our molecular orbital diagram here, and we're going to talk about this a little bit more in a couple of slides, we have a distinction between the bonding molecular orbitals and the anti-bonding molecular orbitals. So if we take 6 isolated p orbitals, each one of those carbons is donating 1 electron into the pi system. Okay, each carbon is donating 1 electron in its p orbital into the pi system. So therefore, if it's 6 carbons, each one of those is donating 1 electron each, then we have 6 electrons being donated into that pi system. According to the linear combination of atomic orbitals, these 6 p orbitals are going to give us 6 molecular orbitals. Now we're not going to do the calculation here, that's way beyond the scope of this course, to calculate what these molecular orbitals actually look like. But we are going to learn a technique for predicting the position of those molecular orbitals in what's called a Frost circle. We're going to learn that in just a little bit. But notice that we have 1, 2, 3, 4, 5, 6. We have this dividing line then right down the center. So we have 3 bonding molecular orbitals and 3 anti-bonding molecular orbitals. So all 6 of these electrons that were put into the system are now in the bonding molecular orbitals because we get 2 electrons per molecular orbital. That's 2, 4, 6. These are also degenerate orbitals, and so these 4 electrons are in degenerate orbitals. The fact that all of them are in bonding molecular orbitals means that benzene is a stable molecule and that it can exist. Okay? So, not all compounds that have similar look similar to benzene are actually what's considered to be aromatic. And we're going to talk about what features make a molecule aromatic in a couple of slides. But think about this. Benzene is a ring, okay? And it's fully conjugated. It has alternating single and double bonds. But not every molecule that is cyclic or in a ring and has alternating single and double bonds is actually aromatic. It turns out that that's true because of molecular orbital theory. Take, for example, cyclobutadiene and cyclooctatetraene. These molecules will actually quickly undergo reactions with bromine, an addition reaction with bromine, to give us a molecule where the bromine adds across one of those double bonds. And in fact, cyclobutadiene is so reactive that it reacts with itself to form a dimer in a Diels-Alder reaction. And then that dimer is pretty reactive, and it actually undergoes a rearrangement to form cyclooctatetraene. So these molecules are obviously reactive, and they're obviously not particularly stable, and therefore there must be something going on here to make them not aromatic, and we're going to learn what that is. That's because they don't meet the criteria for aromatic compounds. Aromatic compounds have to fulfill these criteria. They have to exist in a ring, okay? In other words, they have to be cyclic. The ring has to be fully conjugated. What does that mean? So let's write down cyclic. It means alternating single and double bonds. I'll just write down double bonds for space. Alternating single and double bonds with overlapping p orbitals. What's that mean? That means they're all sp2 hybridized. So we have to have a ring that's fully conjugated with overlapping p orbitals that are sp2 hybridized. So think about that. We've got this overlapping p orbital, potential for overlapping p orbitals, and it has to be sp2 hybridized. So both of these compounds meet that first rule, okay? So there must be something else that makes them not aromatic. And what that is Huckel's rule. So Huckel's rule says that the molecule must have an odd number of electron pairs. an odd number of electron pairs, which gives it 4n plus 2 total pi electrons, where n is an integer. So it has to meet this criteria also in order to be aromatic. Okay, so these don't meet the 4n plus 2 rule. Okay, so let's look at benzene again, of course, because that's our standard for aromaticity. How many pi electrons does it have? It has 6 pi electrons, because remember there's 2 in each bond. That's 2, 4, 6. So does that meet the 4n plus 2 rule? So if n is equal to 1, so 4 times 1 plus 2 is equal to 6. So if n is equal to 1, then benzene meets the 4n plus 2, or Huckel's rule. Notice also that it has an odd number of electron pairs. 1, 2, 3. These are, each one of these bonds is a pair, so that's 3 pairs. So you can also consider it that way. That's the easier way to think about it. So what do these two molecules have? They have an even number of pairs. So this one has 2 pair of electrons. This one has 4 pair of electrons. So if we try to plug that in for Huckel's rule, this one has 4 electrons. So that would be like 4n, okay, where n is equal to 1. And here we have 4 pairs, so that would be 4n also, where n is equal to 2. Okay, so they're not meeting Huckel's rule because it's not 4n plus 2, it's just 4n. And therefore, these have a special name, and that name is called anti-aromatic. And that anti-aromaticity makes them actually quite reactive. So if we consider that molecular orbital theory, and we're going to learn how to draw these molecular orbital diagrams a little bit later on, then here's what the molecular orbital diagram looks like for cyclobutadiene. We have 4 molecular orbitals, and these two right in the middle are non-bonding molecular orbitals because those 4 electrons, remember we have to put 2 in the lowest energy molecular orbital, and then degenerate molecular orbitals, we put 1 electron in each until we have to go back and pair them up. Well, since there are only 2 electrons left and these are degenerate, we have to put them 1 in each. That makes these 2 molecular orbitals non-bonding, and that's why cyclobutadiene is not stable, and that's what makes it anti-aromatic. Okay. Cyclooctatetraene also meets the criteria. It has 8 electrons, and here's its molecular orbital diagram. So it has 8 molecular orbitals. So that's 2, 4, 6. Now we've filled the degenerate orbitals here on psi 2 and psi 3, but we have 2 electrons left over, so we're going to put 1 in psi 4 and 1 in psi 5 because they are degenerate. So that means the non-bonding molecular orbitals are filled, making cyclooctatetraene anti-aromatic. Okay, notice also, like I said, it meets 4n, not the 4n plus 2 rule. It does not meet 4n plus 2. It does not meet Huckel's rule. It has an even number of pairs of electrons instead of an odd number, making it anti-aromatic. Okay, it's so unstable that it actually won't be planar. It adopts a tub shape in order to avoid being anti-aromatic and being unstable. So it doesn't actually act as an anti-aromatic molecule. These double bonds just don't overlap to avoid anti-aromaticity. So it forms a tub shape in order to avoid overlap, and so each one of these bonds just acts like a single bond. They're not conjugated with each other. So how do we determine aromaticity again? Alternating single and double bonds in a ring. Okay. Odd number of pi bonds or electron pairs. And we're going to see that that doesn't always mean pi bonds. And we can't have any breaks in aromaticity. So we can't have any sp3 hybridized atoms in the ring. We're going to see that we have to have a full ring of sp2 hybridized atoms, or a full ring of overlapping p orbitals would be a better way to say it, in order for a molecule to be aromatic. So if we have any breaks in that pi system, it's not aromatic at all. It's not anti-aromatic in that case. It would be non-aromatic. And we're going to look at some examples of that. Okay. Alright, so let's determine whether each of the following compounds would be aromatic. So to do this, they're a ring, and these are all sp2 hybridized all the way around the ring. There are no breaks in that hybridization. Okay, there are no breaks in the p orbitals or in the pi system with an sp3 hybridized carbon. We're going to see a little bit later on. So the only thing here we're looking for is odd number of pi bonds, or an odd number of double bonds. Okay, so I'll just write, I think, double bonds here. I'll write double bonds. Okay, so here we have 1, 2, 3, 4, 5, 6. That's even. Okay, so that's not going to meet Huckel's rule. How many electrons do we have here? Because we have 6 double bonds, we have 12 electrons. Okay, that's not going to meet 4n plus 2. Okay, that's going to meet a 4n, where n is equal to 3. Okay, so that molecule is anti-aromatic. What about the next one? 1, 2, 3, 4, 5, 6, 7. That has an odd number of double bonds, so that molecule, if it's planar, could be considered to be aromatic. And so for my students, I would want you to assume that any molecule that could be planar would be planar. And that's the other thing. In order to have overlapping p orbitals, the molecule must be planar. It must be flat. Okay. So what about this one? Well, let's go back. Let's look at benzene again. So that's another thing about benzene. Benzene is flat. Okay. It's flat in order to allow these p orbitals to overlap. In order for them to overlap, the molecule must be flat. So let's look at this one. 1, 2, 3, 4, 5, 6, 7, 8. That's an even number of double bonds, and so that would be anti-aromatic. Okay. Alright, so how do we draw one of these molecular orbital diagrams? Well, it's really not hard, because you can use something called a frost circle. So in the first step to draw a frost circle, we draw a circle and inscribe a polygon in it that matches the polygon that you would draw to draw your molecule. So this, in fact, is a 7-membered ring here. 1, 2, 3, 4, 5, 6, 7. Well, did I draw that right? 1, 3, 4, 5, 6, 7. It's a 7-membered ring. You inscribe that number of carbons, the ring including that number of carbons, inside your circle with one of them pointing down. You must have one of the carbons pointing down. Doesn't really matter which one, because if one of them is pointing down, this will work. And then you draw a horizontal line across each of the intersections of the carbon. So wherever you have a carbon, draw a horizontal line. Okay. Then you're going to draw a dotted line right down through the center to differentiate your bonding molecular orbitals with your anti-bonding molecular orbitals. And then if you want to, you can erase the circle and the polygon. I usually just leave them there. And then anything below the line will be bonding, and anything above the line will be anti-bonding. If some of your electrons end up on the line unpaired, then they're considered to be non-bonding. Okay, so here's what the frost circles look like for all of the molecules. This is a 4-membered ring. Notice we have the polygon inscribed with one of the carbons facing down. Here's a 5-membered ring like Cyclo, Pentadienyl, but that's not by itself aromatic. That's what I could think of that would be 5-membered. Here a 6-membered ring with one of the carbons facing down. Here we have a 7-membered ring with one of the carbons facing down, and so on, 8, 9, and 10. Okay, so here we have one potential bonding molecular orbital. Here we have 3. Here we have 3. Here we have 3. Here we have 3. Here we have 5. And here we have 5. So this gives us an odd number of bonding molecular orbitals, which is also required for aromaticity. Okay, so we need that odd number. Alright, so again, an aromatic compound has to be a fully conjugated ring with overlapping p orbitals, and it has to be planar. It has to be flat. Okay, and it has to meet Huckel's rule with an odd number of electron pairs, or 4n plus 2 total pi electrons, where n could be any integer. Anti-aromatic compounds fulfill these criteria: a fully conjugated ring with overlapping p orbitals, but they have an even number of pairs of electrons, or 4n pi electrons. Okay. So some compounds that are fully conjugated are larger than benzene. These are called annulenes. Benzene, in fact, is 6-annuline. Here we have 10, and here we have 14. So some of them can actually be aromatic, but let's consider whether they are or not. So benzene has 3 pi bonds, so that's odd. 10-annuline has 1, 2, 3, 4, 5, so that's odd. And 14-annuline is 1, 2, 3, 4, 5, 6, 7, so that's odd. So all of these could potentially be aromatic. Now, this slide is telling you that 10-annuline is not aromatic or anti-aromatic, and the reason for that is because there is some steric hindrance here that forces this molecule into a non-planar conformation, and that's really beyond the scope of what I want my students to fully understand. I wouldn't expect you to be able to predict that. If it's planar, if it's a ring, if it's conjugated, if it has an odd number of double bonds, I would expect my students to be able to predict that that would be aromatic, and that would be the cutoff for them. Now, your teacher may have different criteria for you if you're not one of my students, but really, if it's a ring, if it has alternating single and double bonds, if it has an odd number of double bonds or electron pairs, then you could assume that it would be planar and aromatic. But if it's not planar, it isn't going to be aromatic, in fact. Alright, and some rings can actually become aromatic by carrying a charge. Here's a 5-membered ring. Okay, this 5-membered ring can accommodate the 6 electrons that are required for aromaticity in this type of ring system. And so how can that happen? Well, this is cyclopentadiene before it becomes an ionic species. But if it loses a hydrogen, then it's going to have a lone pair that can be conjugated with an adjacent double bond. So we can draw a resonance structure to puts that lone pair all the way around the ring, okay, and shows the conjugation. So what does that mean? It means that cyclopentadiene is actually pretty acidic, because if you pull a hydrogen off, you're going to get that lone pair on that carbon, meeting Huckel's rule, the 4n plus 2 pi electrons, because that's going to be 6 pi electrons, okay, where n is equal to 1. It's also because this lone pair is 2 electrons, so that's 2, 4, 6. So that's 6 pi electrons, but I was going to say that's also an odd number of pairs. Okay, because that's 1, 2, 3 pairs. 3 pairs. Okay, so that's an odd number of pairs. Versus something like ethane. Remember, ethane is like the worst acid ever. It's got a pKa of 50. And so it's never going to lose a hydrogen by itself. You have to do something to make a base out of this thing. But in fact, cyclopentadiene is fairly acidic because with a pK of 16, because it becomes aromatic when it loses that hydrogen. It gets a lone pair on that carbon and becomes aromatic. We can draw resonance structures for that aromaticity. Okay? So a 7-membered ring, can it actually become aromatic if it isn't to start with? Or would it be to start with? That's a good question. So let's look at what a 7-membered ring actually would look like. Let's draw one over here. Okay, now let's think about putting some double bonds in there. So let's put a double bond here, double bond here, double bond here. So we got this carbon right here kind of left out. We can't put a double bond here because that would be overlapping with this other one. That would be like a accumulated double bond, right? So this carbon here has to be sp3 hybridized. Okay, can't have an overlapping sp2 hybridized system. But can we do something to make this thing aromatic? Because if these are our bonding molecular orbitals here, then we can only put 6 electrons in there, right, to have something be aromatic. So what can we do to basically make this molecule aromatic out of the 6 pi electrons that already exist? Okay, what can we do? Well, what if this wasn't a hydrogen? What if it was something like a bromine? Okay, what do we know about these types of molecules? They can undergo a type of reaction called an SN1. Let me erase that. That's confusing. Where what happens? The bromine just kind of picks up and leaves on its own. And a molecule like this would be particularly apt to do that because what's going to happen? Once it picks up and leaves, then let's put our double bonds back. Then this becomes a cationic species. What do we know about the cation? It's going to be essentially sp2 hybridized. A carbocation is planar. So that planar carbocation can overlap with the pi system that already exists. In other words, we have an empty p orbital right here. An empty p orbital that can overlap with the pi system that exists in the rest of the molecule. So by forming a carbocation on a 7-membered ring, we can make that molecule aromatic. Does it meet the criteria for aromaticity now? Yes. It's all in a ring. It's sp2 hybridized. Okay, so it's planar. It's in a ring, it's sp2 hybridized, and it has 6 pi electrons, which means that it meets Huckel's rule for 4n plus 2, where n in this case is equal to 1. Or we have an odd number of electron pairs. 1, 2, 3 pairs means that it can be aromatic. Okay, so this molecule is aromatic. Now sometimes we might have a compound that may contain something other than carbon inside the ring. So for example, let's consider pyridine and pyrrole. So pyridine has the nitrogen double bonded with an adjacent carbon. So we have a double bond here. That's the nitrogen has donated 1 electron into that pi system. Each one of these carbons has donated 1 electron into that pi system. Okay, so nitrogen has 1, so it's forming a double bond here. These 2 carbons have donated 1 each. These 2 carbons have donated 1 each. So with that nitrogen's 1 electron, so let's look at it down here, 1, 2, 3, 4, 5, 6, then these electrons are now delocalized around that ring. Okay, so that means that in this case it's sp2 hybridized, it's planar, okay, it's cyclic, okay, and it meets Huckel's rule. We have an odd number of electron pairs. So this molecule is in fact aromatic. Okay, and what about this molecule over here? The nitrogen in this case for pyrrole is donating a whole lone pair of electrons to the system instead of just 1 electron because it's not double bonded. Okay, that lone pair is being donated into this pi system here. It's not double bonded, but the carbons are double bonded, and therefore the pi system can overlap with that lone pair from the nitrogen allowing this molecule to also be aromatic. Now we have 2, 4, 6 pi electrons. Okay, so that's 3 pairs. So that's an odd number of pairs. It's in a ring. Okay, it's all sp2 hybridized essentially because this nitrogen's lone pair is being forced into that ring system, making the bond angles for this conform to sp2 hybridization. So this is actually planar because that lone pair overlaps with the pi system, okay, and it actually this hydrogen then would be perpendicular to that pi system, okay, making this molecule aromatic. Okay, but notice this lone pair is participating in aromaticity here, but it isn't here. And now in this molecule on the left, it's actually in pyridine, it's actually sticking out to the side. The lone pair is perpendicular to the pi system. So what does that mean? It means that for something like pyridine, it actually can act as a base, whereas the lone pair in pyrrole is not basic. Because it's within the pi system, it's tied up with aromaticity, it's not going to act as a base. Whereas in pyridine, the lone pair is perpendicular to the pi system. If it picks up a hydrogen, it's not going to affect the aromaticity at all. So let's see what that looks like. If the nitrogen in pyrrole picks up a hydrogen, we get this species here that's positively charged. It actually is still aromatic. But for example here, if pyrrole picks up a hydrogen, then it becomes non-aromatic because it loses the aromaticity. So pyridine can pick up a hydrogen and still be aromatic, whereas pyrrole picks up a hydrogen and loses its aromaticity. So that's going to affect the pKa. The pKa of pyridine is actually 5.2 and pyrrole is 0.4. We can observe where these electrons lie if you look at a electrostatic potential map for each. For pyridine, the lone pair is located out to the side, it's localized, and for pyrrole, it's delocalized around the entire ring. Okay, so let's determine whether each one of the following ions, now we're figuring whether ionic species are aromatic, non-aromatic, or anti-aromatic. In other words, having a charge, can that affect whether the molecule becomes aromatic or not? Okay, so here we have this I'm sorry. Okay, so here we have this cyclopropenyl cation, anion, I'm sorry. So is this thing going to be aromatic, non-aromatic, or anti-aromatic? So for this molecule, we have 2 pairs of electrons, and so that's even. Okay, even though it's in a ring. And so that's going to be anti-aromatic because it meets the 4n rule. It's not 4n plus 2, so that makes it anti-aromatic. What about this one? This is also a cyclopropenyl ionic species, but this is a cation in this case. So this has 2 electrons. So that's 1 pair. So it actually has an odd number of pairs of electrons, and so that molecule is aromatic. So for the next one, we have cyclopentadienyl cation, and so that gives us 4 electrons. That's 2 pairs, so that's anti-aromatic. And for the next one, we have this molecule that's larger, and it has 1, 2, 3, 4, 5 pairs of electrons, and so that's odd. So if this molecule is planar, which for my students you can assume that it is, that's going to make this molecule aromatic. Okay. All right. So you can see here that we can have other molecules that have heteroatoms in the ring. So are they going to be aromatic, anti-aromatic, or non-aromatic? So here we have a nitrogen double bonded to the carbon next door. So that means this lone pair, by the way, is sticking out. It is not, it's perpendicular to the ring. Okay, so that means we have 2, 4, 6, 8 electrons. That's 4 pairs. So that's anti-aromatic. This one has one lone pair that's perpendicular to the ring and one lone pair that can be within the ring system. So one of those lone pairs is going to be perpendicular. That forces the other one up into the plane of the ring. That gives us 2, 4, 6, 8 electrons. That's 1, 2, 3, 4 pairs of electrons. And so that's anti-aromatic also. This one has 1, 2, 3, 4, 5 pairs of electrons. So if this molecule is planar, and for my students we can assume that it is, then it would be aromatic. Okay, and for the next one we have 1, 2, 3, 4 pairs of electrons, making it an even number of pairs. So that's going to be anti-aromatic. So for these, we want to determine whether the lone pairs are participating in aromaticity. So for this molecule, which is furan, we have one of the pairs of electrons on the oxygen that can be in the ring with the other, probably should draw this with a different color, right? The lone pair is forced up into the ring with the double bonds, and so this molecule is aromatic, and one of those lone pairs is participating in aromaticity. The other one is perpendicular to the pi system. So if we look at that on its side, let's draw the oxygen in the front. Trying to draw it kind of on its side. Then one lone pair is going to be in the contributing to aromaticity with the p orbitals, overlapping with the p orbitals in the ring. Okay, and the other lone pair is going to be perpendicular to the ring, sticking out. Okay, so let's look at that same molecule with a sulfur. We're going to have the same thing. If we had a sulfur here instead, it would be just the same. So one of those would be participating in aromaticity. For this nitrogen, let's see, we've got a lone pair here that's going to be forced up into the ring, and a hydrogen that's perpendicular to the ring. So that's going to be 2, 4, 6, 8 electrons. 1, 2, 3, 4. 4 pairs. So that's even. So that's not actually participating in aromaticity because that molecule is anti-aromatic. Okay. What about this one? The sulfur can have one pair participating in aromaticity and one pair that is perpendicular. So that's going to be 1, 2, 3 pairs of electrons. This nitrogen, the lone pair is perpendicular to the system because it's double bonded to this carbon. It has to be perpendicular. So that's going to be 3 pairs. So this is aromatic. One of the sulfur is going to be participating in aromaticity. The nitrogen's is not participating in aromaticity. So for this oxygen, we've got an oxygen double bonded to a carbon next door. So that means the lone pair has to be forced perpendicular to that. So we have 3 pairs of electrons. This molecule is aromatic, but the oxygen's lone pair is not participating in that aromaticity. I think I will let my students figure the rest of them out, and I'll go ahead and move on. Okay, so some molecules, other than benzene, these polycyclic molecules can also be aromatic. We have naphthalene, anthracene, phenanthrene, and we can demonstrate whether they're aromatic using heats of hydrogenation. So we have stabilization energy of 152, 128, 115, 127 kilojoules per mole. So these are a little less stable than, say, benzene, but how many double bonds do they have? So this is 1, 2, 3, 4, 5. That's an odd number, so that could be aromatic. 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7. So that's an odd number. 1, 2, 3, 4, 5, 6, 7. So that's an odd number. So all of these molecules can be aromatic, but they have a little bit lower stabilization energy per ring, okay? Just because of the fused ring system is somewhat less stable. Okay, so they're not as stable as benzene per ring, but they are still aromatic and they still have aromatic stabilization energy. Okay, so we already talked about that. Alright, so let's talk about reactions at the benzylic position next. I'm going to go ahead and stop here and start another video where we're going to talk about reaction at the benzylic position.